Hi everyone, welcome back. My name is Grace, and my degree in aerospace engineering has officially been conferred. My research was on trajectory planning and mission design for cislunar space operations. I defended back in December and submitted my final dissertation in February, but Cornell only confers degrees 3 times a year, so I had to wait until the end of May to actually get the diploma. But now I can finally call myself a doctor at really inopportune times, like on a plane when someone needs life-saving medical care. So it is now June. The last gymnastics practice was about a month ago now, and instead of my usual filming footage for actual analysis, I decided to use it as an opportunity to take graduation photos. It was a lot of fun getting to play around in the gym, but figuring out how to move around in graduation robes was hard. Eventually, I did get some good action shots. Anyways, this week I thought I'd talk about forces, and we'll start with the idealized rigid body dynamics that you first start out learning about in physics class. In this model, you have a single mass, which is me, reduced to a single point, otherwise known as a point mass. One of the first diagrams you learn about in physics is the free body diagram. Typically, you represent your point mass as a block in some reference frame. Here, we'll define an inertial frame, which means a frame that's not accelerating and Newton's laws apply. We'll also define the coordinate vectors for this frame, the x-axis running left-right, and the y-axis running up-down. Now we can draw the forces the mass, in this case me, experiences. In this simplified model, we'll stick to the two that are the easiest to model, the gravitational force and the spring force from the tumble track. The force due to gravity is F equals negative mg y hat, where m is the mass of me, g is the gravitational constant at sea level, and y hat denotes the direction the force is acting. The spring force is F equals negative k delta s hat. K is the spring constant, which is basically how springy the spring is. Spring constants are measured in force per length, so you can think of K as how many pounds of force needed to stretch a spring 1 foot. So at rest, the end of the spring is at some location. Then, say you pull on the spring. Now the end of the spring has been extended out some amount away from its rest position. The distance between the two is delta s, and this displacement happens along the s direction, which is not necessarily perfectly aligned with x or y. It could be a little bit in x and a little bit in y. These hat and bar terms are called vectors, and vectors have both a magnitude and a direction. The magnitude tells you how much, and the direction tells you where. Now, a little more syntax before we get back to forces. The bar is for a vector of arbitrary length. It could be 1, or it could be something else. The hat is for vectors with a known designated length of 1, and sometimes you'll hear this being called the unit vector. So we named a few terms when talking about the gravitational and spring forces. Some of these terms we know outright or can be directly measured from the data, but the spring constant isn't directly obtainable. Luckily, we can calculate it. At rest, when I'm not moving, the gravitational and spring forces are equal and opposite each other. Gravity is pulling me down, and the tumble track wants to push me up. I'm at rest, which means I'm not accelerating, so the force balance is 0 equals force gravity plus force spring. After some algebraic manipulation, we get 0 equals negative mg plus k delta s. We can then further rearrange it and get mg equals negative k delta s. My mass and the gravitational constant are known, and the spring displacement we can measure. We'll record my ankle when my foot is just barely touching the surface of the tumble track, so I'm not activating any of the springs. We only care about the y component, so we only need the 10.97 centimeter value. Then we can see where my ankles are when I'm just standing on the tumble track. We only care about the y component, so we only need the 5.364 centimeter value. That's how much I displace the tumble track at rest from only the force due to gravity. We'll take the difference between the two and get 5.606 centimeters. So now we can isolate k and solve for the spring constant. So here are all of our known quantities. M, my mass, is 47 kilograms. G, the gravitational constant due to gravity at sea level, is 9.81 meters per second squared. And the spring displacement is that 5.606 centimeters we just solved for. So now we can plug in all the values, and we get 8,225.581 newtons per meter, or 563.563 pounds per foot. Now we can apply this to some snapshots in time. As I'm going through a tumbling pass, the assumptions that are baked into idealized rigid body dynamics fall apart. And this is because as I'm going through a tumbling pass, there are internal additions and losses of force based on how good my form is and whether I'm preparing to land a skill or prepare for the next one. So we'll only look at the spring force at certain points in time. So here's the force I get coming out of the roundoff and into the back handspring, about 183.03 pounds. And the force I get coming out of the back handspring and into the back tuck is 256.69 pounds. When I change the back tuck into a layout, the force coming out of my back handspring is roughly 290 pounds. For reference, these values range between 1.8 to 2.8 times my body weight. Anyways, thanks for clicking and watching. I hope you found this fun, entertaining, and educational. If you like this, please consider liking and subscribing for more post-PhD and physics of gymnastics fun. Until the next one, best regards.